Hey guys, so this is a bit of a shorter lesson for section 11, 11.3, the normal distribution. We're going to focus mainly on the empirical rule for these questions because that's what your e-learning quiz is going to be on. However, we are going to go into using your graphing calculator to use the normal CDF function. Those of you who have some stats background, you know what I'm talking about. All right, let's talk. So I'm clearly recording from home, which means I have children who are probably going to run in at some point. And we'll make do. All right, so our normal distribution. Big idea today is, can you use the empirical rule to calculate the probabilities with given information? We are going to talk a little bit about Z-scores, which is how we standardize our data. And then we are going to talk about the calculators as well. All right, I'm going to try my darndest to keep this video short if things will work. All right, here it goes. So if you have the worksheet printed out, this is officially worksheet 12, but the ideas are going to be the same if you have something older to look at. The graph is a bell-shaped curve. It's symmetrical with respect to the mean. The mean is right in the middle of it. The idea is underneath this curve, it's 100% probability, technically, although it's continuous and it doesn't end. So that's kind of a weird idea. It approaches the x-axis, but like we said, it kind of an asymptotic behavior, so it doesn't connect with the x-axis. And we consider the area under the curve to be 100%, which we notate as 1 in probability land. So that's some ideas there. And it did, on that slide, Mrs. Hoffbauer had some writing about mean, median, mode being the measure of central tendency. For these curves, we're going to refer to the population mean. So the idea is they're going to normalize the data and assume that whatever we're talking about works because it's behaving like the entire population does. Here's some cool graphics from your book. Talks about what happens when you adjust the mean for two sets of data versus whether you have a larger or smaller standard deviation. And I know there's been a lot of talk lately about like flattening the curve. This isn't quite the same kind of curve that they're talking about in the news, but similar idea in math. You get different behaviors based on your data. So this right here, this is the empirical rule. And if we were to test you traditionally, we would give you a beautiful formula sheet. And what's a little deceptive about this particular piece on the formula sheet is there's a missing component. So when I do all my problems, okay, after teaching this for like 13 years, I finally figured out that I can't draw. Okay, let's be honest, I knew that. So now that I've accepted that I can't draw, I've just kind of I've stolen an image off the internet basically to help me with all these problems. So the idea for the empirical rule is you have the mean in the middle. And if you go one standard deviation above or below it, you're looking at a total of what's called 68% probability. So there's you either can interpret it as 68% of the data falls within that category, or a 68% probability that you are within that range. So it extends further out. If you go 2 deviations out, you're looking at 95%, and then 3 deviations out, you're at 99.7%. So almost the entire probability curve. This is where it's a little deceptive. It's not quite 100, is it? So we've said this curve determines to be 100%, meaning that there's 0.3% that exists in these teeny tiny little tails that are out here. So in each one of these tails, it represents 0.3% cut in half. So I'm going to kind of adjust this and say it's 0.15%. That's supposed to say percent. You can't read that though. 0.15%. So that's really teeny tiny. But it is, you know, it makes a difference in our math. So I'm going to put it down there. I should caution you that the empirical rule is just that. It's a rule of thumb and it's not perfect. And we're going to talk about how the calculator and the empirical rule will differ a little bit. And in the grand scheme of things, usually doesn't matter for us. But if we were doing really important work, we'd probably want to not just use a rule of thumb and use the actual calculation. Huh? All right, let's talk about these other percentages. So this guy here, this 95% exists from 2 deviations out, right, here to here, which means that within these 2 red lines, you've got 95% of the data or probability there, which means 5% exists on the tail. So I'm going to do something really ugly to this curve. I'm going to say from here out and from here out, those are 5%, right? So if you cut 5% in half, you got 2.5%. Well, you notice that number's not actually on this diagram. That's because of those teeny tiny tails. So they took off the teeny tiny tails and they said, okay, from 2 deviations to 3 deviations, that's really just a section of 2.35% through a subtraction problem. All right, similarly, let's talk about the 68% data. So from here, man, I can really mess up a picture, can't I? It was even drawn nicely, and look at me, messing it up. All right, so Abruzzo subtract. All right, 100% minus 68% would be 32%. So that means we got 16% on each side, right? However, you'll notice that 16% is not a piece of this little graphic, because what happens is they took the 16% and then they cut it off at the 2.5%, the red line. So from here to here, 1 deviation to 2 deviations out is really just 13.5%. And then, it's not really a big mystery anymore that 68% cut in half is 34%. You probably saw that one right away. But that's where these little chunks are coming from. So there's a lot of ways where we can teach you how to use the empirical rule, but for me, I don't know if it's just because I'm home, my brain's like in 12 different places. It really helps me if I just think about which chunks I'm using and I just add them all up. So if you can come up with a quicker, a shortcut, by all means, guys, use it. My technology's not behaving for me right now, so I'm getting a little frustrated. And if you can hear my kids laughing and having a good time back there, I'm sorry. I'll go yell at them in a minute. All right, so this is the graphic I stole from the internet that I'm going to keep stealing basically for the first few problems here. And the reason is because I can't draw normal curves. You're going to have to draw your own curve. So sorry about that. Not for these first 2 examples, though. I don't even think these are on your page. These are just for you to watch. These are from your textbook. So using the empirical rule, we're going to give you some information, and it says we have 880 students, so we'll just call that the population. That comes in later. They're normally distributed, the heights are, with a mean of 67 inches. So you'll notice they put the 67 smack dab in the middle of your curve. And then a standard deviation of 2.5 inches. So if it was me, I would have drawn a really ugly curve and then started measuring up 2.5, counting by 2.5s. So that's where the 69.5 came from. They added 2.5. And then they added another 2.5. And they got up here to 72. So the reason they went that direction as far as labeling the curve is because the question is, how many students are more than 72 inches tall? So according to the empirical rule, this little piece here, if I go back to my slide here, my face is in the way. All right, hold on. That was this guy. Ooh. Okay, that was this guy up. So maybe I kind of remembered the way I broke it down earlier about it being 5% cut in half, but 2.35 plus 0.15 is indeed 2.5%. Now, this is a bit of a trick question because it says how many students. They don't want the answer of 2.5%. What they want you to do is take 2.5%, which we know is 0.025, and multiply by how many students you have, which is 880. And I don't know if it comes out to exactly 22, but your book says 22, so we'll go with it. Probably. Oh, I should be able to do that in my head. I'm a math teacher, but alas. Okay, now my face is really in the way. All right, let's try that. This is another good one from your book. So we have, same question. The height, they're really interested in the heights of these students, huh? All right, just a moment. I gotta yell at my kids. We're back. Okay, so what percent of the students are between 59.5 and 69.5? So that's nice that they already kind of labeled the curve for me. Remember, the mean here was in the middle. This was 67, so they measured up 1 deviation, and then they measured down 1, 2, all the way out to 3 deviations. But remember, that doesn't end. However, there's that little tiny teeny tail here, huh? So for me, and I think they did kind of something similar here, they just added up all the chunks. They took this 2.35, the 13.5, and then instead of 34 and 34, they just called that 68. So let's look at a problem that's not done. All right, so again, apologies. I'm limited in resources, like I can't draw. So I stole this off the internet. The average monthly temperature for a city has a mean of 65. So what I'm going to do on my curve is I'm going to throw a 65 here in the middle. Oh, I can't even write numbers. That's good. And then the standard deviation is 5. So as I measure up the curve and down the curve, I count by 5s. So up 5 would be, that's 70, 75, and 80. And then going down the curve would be 60, 55, and 50. Cool. So the question they have for you is, what's the probability, and that's all they want is probability, between 50 and 70. So here's 50, and here's 70. You're just going to add up all the chunks. So 2.35 plus 13.5 plus, I'm just going to call that 68. I should be able to add some of that on my own. I got 83.85. I didn't key this, which is really dangerous. Oh, wait, I did key this one, maybe. I did. All right, we did well. So that's that. That's how we use the empirical rule to find probabilities. It's really handy when you get to just steal things off the internet for graphics, though, right? Maybe have one of these handy, a really nicely done one when you guys do your quiz later on in the week. So this question's about trees. I love trees. The heights of 200 trees are normally distributed with a mean of 120 and standard deviation of 16. All right. Oh man, this is in the way. So mean of 120 is going to go in the middle. And then a standard deviation of 16, which means I should be able to add by 16s, huh? All right, 136, 152. Did I do this one? I don't know. Maybe. Why am I so confused with my, what do I have here? Anywho, all right, 32, yeah, whatever. I'm going to stop labeling because apparently I can't subtract or add. If I go down 16, this is 104. Uh-oh. And then this is 88. Gosh. I'm going to go on a limb and say I'm good. It matches something on my key from 2 years ago, so we'll count it. All right, here's the point. I don't know that I really needed all the information because what does it want from me? It wants how many trees are more than 136 inches. So 136 would be this line right here, and then more than 136 would be us adding all this up. Now, of course, there's an easier way to kind of simplify me adding up these three pieces, but, well, it's 16%. But this is where kids get in trouble because they just call it 16% and then they say, like, that's my answer, but they want how many trees. So remember, there were 200 trees in this nursery. So 16% times 200 is 32 trees. That says trees. All right, what percent? Now they're switching on you. What percent are between 88 and 104? Oh, well, that's actually a really easy question. Is that really all they wanted? All right, 13.5%. So this is kind of the beauty of, you know, having a handy empirical rule with you, because it's, once you understand how to use it, it's actually pretty easy. Unfortunately, it's not super accurate. All right, which brings us to our next topic. Okay, it's pretty accurate, like accurate enough for what we're doing. How's that? So this idea is standardizing data and changing raw data into what we call a Z-score. So that same empirical rule, if you can convert everything to what's called Z-scores, that means everything has a mean of 0, and then standard deviations are ways that you could compare how spread out your data is from one data set to the other. So it's really hard to look at like two different sets of data that are so very different. And you know they're inherently different. So it seems kind of stupid to compare them. Like on my Flipgrid, I don't know if you guys watched it or not, but I compared like high temperature average and low temperature average. Well, like, of course that data set shouldn't look the same. They have totally different means. So rather than comparing them straight up like I did the stupid box and whisker plot, you know, what would happen if we collected a lot more data and we standardized the data, or we looked at data over time, you know, things like that. So Z-scores, a really simple formula, and really not that hard to use. So what you do is you take whatever the statistic, the measurement that you have, you subtract the known mean and you divide by the population standard deviation, and that's called a Z-score. So you're essentially figuring out how far away from the standard mean you are, whether you're above the mean or below the mean, and you're converting it to a standard parameter. All right, here we go. the z-score. Find it. All right, so find the z-score if you've got a mean, nope, not mean, a value of 65, and your population mean is 50, right there. So already you can tell you're above the mean, which means you should have a positive z-score, and your standard deviation is a 10. All right, so like that's 15 over 10, so 1.5. So here's what this means to me. Oh, I said I wouldn't do it, but here I go. I'm going to draw a really ugly curve. You got your mean in the middle. For standardized data, our mean would be 0. And then you've got like 1 deviation up and 2 deviations up. And your particular information here, your value of x equals 65, is 1.5 deviations up the curve. So it's like roughly right here. So this is going to be really helpful when we're looking at values that are not necessarily on the empirical rule, like it doesn't fall exactly 1 deviation or exactly 2 deviations away from the mean, and they fall in between. All right. So this one is kind of backwards, right? So this time they don't tell you the x value and they give you the z-score. So the z-score is negative 0.4. And then we don't know the x value. That's what we're trying to look for, the statistic. The mean is 40. And then your standard deviation is 5. All right. So then we'll do a little fancy work. I'm going to be honest on my calculator because I'm tired. So I'd multiply by 5. I'd multiply this by 5. Negative 2. I said that like a question. It wasn't really a question. I think it's right. And then I'd add the 40 over. And we find out that the value here is 38. Fingers crossed. Check the key. I didn't answer it on the key, so I don't know if I'm right. Let me double check again. What was I wondering? 5 times negative 0.4? It's totally negative 2. Go me. All right. So, and this kind of makes sense because if I try to draw another, no, I'm just going to use the ugly curve I already have. If your mean was at 40, so pretend 40 was in the middle here, 38 would be, down a little bit and not quite 1 deviation down. And that makes sense with it being a z-score of negative 0.4. That kind of rhymed. All right, so let's talk about what z-scores look like on the curve. I kind of already spoiled that for you on that last question. They look the same. Here's why z-scores were such a big deal back in the day, and they are still a big deal. They're very useful in probability. Like I said, it's good for comparing two sets of data, that have clearly different means and deviations, but how can you compare them next to each other when they're inherently different? And the idea is you standardize the data. So this little picture up here in the upper right corner, this is like giving me flashbacks to Mr. Dredge's class, like a long time ago. I had Mr. Dredge for stats, and we had to open up to the back of the book and find, our z-score value and add up whatever we needed to add and subtract whatever we had to subtract. And it was like mind-numbing. And I'm not that old, guys. Like, we had graphing calculators back then, but we had to learn both ways. And I'm really glad he made me learn both ways, because then I went to college and then I had a professor who refused to let us use calculators. So it was worth it. It was a struggle, but it was worth it. There's a lot of questions that they ask as you go on to like upper classes, where you can't use your calculator on them because there's some sort of variable within the formula, and the calculator's not going to help you. So I'm not going to say you have to look up in charts really much in your future, but the fact that you know what a z-score is and how it relates to standard deviation and mean, I think would be really important. Now, something else on the screen, we got normal PDF and normal CDF, which we're going to find in the distribution menu of our calculator. It's the same menu you went to when you did binomial PDF and binomial CDF possibly on a previous lesson. But these are the first two in the menu because they're most frequently used. So CDF is the one that we're going to be using today, because what it does is it accumulates all the probabilities and it adds them up from point, whatever to point whatever. When you're working with z-scores and they ask you for something like a lower bound or upper bound, the idea is you just put, like, if it doesn't, that curve doesn't end, right? So if you need something like way far to the left, you just put like a ridiculously left negative number and just call it good. I'm a big fan of negative 99999, works for me. All right, so it does show you as a little tip from your book. We're about to go over that in a minute. This is an example from your notes. So here's where those of us who have some stats background, they're going to be like, why are you making me do this? So an employee had an average layover of 82 minutes. Okay. So that's the mean. Oh, that's a mu, by the way. I don't know if we ever talked to you about that. That's a Greek letter mu. Mu. All right, standard deviation of 7.5. That's this guy, sigma. Find the number of layovers that were less than 75 minutes. So when we get to it, we need to figure out less than 75 minutes. Now, the empirical rule is not going to work for us here because if I subtract 7.5 from 82, I'm not going to get to 75 exactly. So what they did is they calculated it as a Z-score, and then they went ahead and did what's called the normal CDF. All right. So you see the Z-score calculations. That's not like a big mystery, right? So envision this. You got, that's the middle. You got your standard normal distribution curve, and you have a Z-score of negative 0.93, which represents the 75 minutes thing right here. Okay. And they want to know what percent, or eventually what number, I think, are less than. So they want this probability right here. Okay. So on your newer calculators, which is what most of us are working with now, we have a really cool thing where it asks us to be, it prompts us. Okay. Ooh, where'd you go, calculator? Come back. All right. So we go to distribution. So second varies. And then normal CDF is what you want to use here because I remember it as accumulating all the data, adding it up. And then these are the prompting screens. So lower bound, it defaults to negative 1e99. That's like negative 1 times 10 to the 99th power. It's pretty small. I don't know. Fine, you can leave it. If you played with that number a little bit, it might change some of the far out decimals. All right, so the upper end point there on that curve, which I lost my whole file here. There we go. Was a Z-score of negative 0.93. Lesson's not going as smoothly as I want, but I hope you're getting a good laugh out of it. Now, because it is a standardized curve using a Z-score, this calculator kind of puts in a 0 and a 1 for the mean and the standard deviation. So that's kind of nice. That's the understood default setting for your calculator. And then you notice once I hit paste, it goes ahead and pastes it into the order that you would need it on one of the older calculators. So this is one of the cool upgrades they did back in the, I don't know, last decade, I guess. So lower bound, comma, upper bound, comma, mean, comma, standard deviation, and then we get, voila. So 17.6%. Let me show you something though. So same thing. Normal CDF. Let's say I never standardize my data. So lower bound. I need something super far to the left of, was it 75? 75. So actually what I had I could have kept. So upper bound of, I think it was 75. I'm going to look like a big dummy if it doesn't work out. I already forgot what the rest of it was. All right, the original mean, remember, was 82 with a standard deviation of 7.5. So if I don't standardize the data, and I have the memory of more larger than a goldfish, and I actually remember things, pretty much the same thing, guys. Yeah. I have a feeling, what is this? 5. Did they round this? They must have rounded it a little bit, right? 75 minus 82. I can't even subtract today. Or any day. Who am I kidding? This is not new. I'd like to blame this on my, yeah. Okay, so right there, by them saying the Z-score was negative 0.93 and then truncating the decimal, they've inherently kind of accepted some, it's wrong. No, it's not wrong. They're close enough is what we're going to do. So let me tell you, for PreCalc Prob and Stats unit, we don't expect like amazing, miraculous answers. What we expect is, do you understand how the empirical rule works from the first few slides? And then now, could you also maybe double check it or even take a shortcut using your calculator? What we just learned in this example is, while yes, we can standardize the data, but if our only true reason for standardizing the data is just to get some probability calculation, you don't have to, okay? Now, I didn't finish the problem. Remember how it was 17.6%? We had to go and multiply it by the number of airplane trips that he took, also known as flights. So 20 times 17.6% is about 4 flights. And again, that's a discrete number. I will use a vocab word. So I couldn't say like 3.9 flights. So even if I was a little off on the probability, like it's potato tomato, as I like to say. All right, so let's talk about this example here. And I think we can all understand that the stuff on the calculator is kind of awesome. And knowing that we don't have to change it to Z-scores is kind of nice. Maybe on this question, I'll do them 2 ways, and then maybe I'll stop. All right, at a restaurant, the average ticket time, blah, blah, blah. All right, so here's the average. There's your mean. Standard deviation of 1.2. And then your sample size is 100. And they want to know within 14 minutes of ordering. So 14 minutes or less, right? So if I wanted to standardize this, which I sure could. Oops. 14 minutes would be the statistic. The mean is 12.5. I can't write. All right. And then the standard deviation is 1.2. You know, I really need students near me so they can tell me what dumb things I'm doing at all times. All right, I got a Z-score of 1.25. Makes sense for what I'm visualizing here. And apparently what I'm visualizing is the world's ugliest curve, right? So 1.25 deviations, I'm just going to pretend it's like up here somewhere in the curve. And they want to know the probability are served within 14 minutes. So they want this probability, okay? So on my calculator, I'm going to do that normal CDF thing. And if you have a new one, you're in good hands because it's going to prompt you on all this, but your lower bound just has to be something super duper negative. So like for me, I'm going to go like something ridiculously largely negative, I guess small then if you want to be particular about it. And then your upper bound here, it stopped at, this was a Z-score of 1.25. Now because this was standardized data, you could do 1, 0, and actually what's kind of neat about your older calculators in this case, if you don't put anything in those last two and you just close you hit enter after the 1.25, it assumes that your mean and deviation are, oh, I got that backwards. Hello. Dyslexia. It didn't get better. Okay, 0, 1. Now it's blue. And you're going to get the right answer. So here's my other point though. And this is where my friends from stats are like, why are you doing all this work? This question could have been done the same way. Using a normal CDF. You even could have used the same lower bound. You could have said negative 99999, whatever, anything really negative. And then your upper bound being 14. And then your mean, oh, I ran out of room, is 12.5. And your deviation was 1.2. You can read that, right? And I haven't answered any of these. So I'm going to go to my calculator. I'm going to go figure that out. And if you want to just pull up a new one that works for me, and sometimes this is how I make my decision as to which method I'm going to use. If I've already found the Z-score, see, like here, I don't have the mean and deviation as 1 and 0 or 0 and 1 anymore. So I'm going to go ahead and I'm going to leave the lower bound, of course. Gosh, I already forgot what it was, guys. Mean of 14 and a deviation of 1.2? No, that wasn't right. Oh. You know, guys, I wanted this video to be short. It's not. All right, mean, no, my X value is 14. Mean of 12.5 and 1.2. I'm not going to remember any of that. Oh, God. 14? 12.5? 1.2 maybe? Gosh, be golly. I don't know. Here's to hoping. Alright, well, you know, fun fact, I didn't key this, so I don't know if we're right. I hope we're right, guys. I didn't write down the answer either. Okay, so like I said, 89.4%-ish. Now, we're not done, because it does say, out of the 100 people. Hey, that's an easy math problem, right? So if it's 89.4% times 100, that's about 89 people. I got this. Again, we might be an off by like a person. Like whatever, close enough. Alright, so that's the idea for using your calculator. This question is probably depressing because it's talking about salaries, and I don't really want to talk about salaries right now. Some of us don't get salaries. I mean, I do. Maybe you don't. Alright, anywho, I'm kind of looking ahead, trying to decide. Let's do one more. You know, apparently I have a passion for temperature, so let's do number 6. Alright, during 1 October, the average water temperature of a pond was 53.2, with a standard deviation of 2.3. How many days? Now, October is 31 days. I had to sing a little song in my head. So keep that in mind. Is the temperature greater than 50? So here's what I'm thinking. I'm going to use my normal. I'm not even going to go to Zscores anymore. I'm going to use my normal CDF. Was the temperature greater than 50? So be careful here. This time your lower bound was 50. And then for your upper bound, put something ridiculous in. Put positive 99999. Like, no. Is your temperature going to get to that? No. But just, it's okay. All right, your mean average, there we go, 53.2. And then your standard deviation is 2.3. And then I just crank that in the calculator. And since I don't want to embarrass myself in front of the internet again, I'm just going to do this on my calculator. And that way when I'm wrong, you could be like, it's a mystery. I don't know what she did wrong. I hope y'all are able to get a emulator on your Chromebook. We posted like a link where you could get free one until it's good till August. So maybe they'll extend it to our district, or at least we'll buy something from them. All right. I was wondering what this question was about for a minute. It's water temperature. I got really excited for a minute. Water temperature. Okay, so the probability I got is roughly 0.918, so 91.8%. How many days of that out of the whole month of October? So 31. 30, September, April, June, and November. We have all the rest of 31. And Halloween. Hello. All right. So anyways, here's what I'm coming up with. About 28 days. Now, if you want to justify it to yourself, you could draw yourself a little normal distribution curve and see if it makes sense. I'm sure it makes lovely sense. All right. I know that was comical. I appreciate you watching. You have some practice work. It's actually not a lot of work. It's just a couple questions on each worksheet. And now that we know that there's a bit of a trick to these, that's awesome. You have a quizzes coming up. That's really cool. I think it's really neat. They are timed questions. So you want to have like all your materials handy. Like if you want to use one of those pre-made empirical rule ones like I cheated with, make sure you have that handy, and of course have a calculator handy. You don't need anything fancy for the empirical rule, and actually the whole quizzes could be done using the empirical rule, so keep that in mind. All right, good luck everybody. I miss you.